In this video, I want to have a look at limits and what they have to do with continuity. So the idea of continuity is that a function is continuous if we can draw the function without taking our pen off the paper. So if we get a little bit more specific, we say a function f of x is continuous at a particular value of x if the graph can be drawn through that point without any break. So if we have a look at this first one here, this parabola, every point on there, because we don't have to lift our pen off the paper to draw that curve at all, that whole curve is continuous everywhere. If we have a look at our next one, our hyperbola, this one we've got two sections of our graph. So we do have to lift our pen off the paper to draw that. And the point where we have to lift it off the paper is at the point x equals 0. So this curve is continuous everywhere except at x equals 0. There's a discontinuity. So similarly with this one, we've got two sections of our graph. So we do have to lift our pen off the paper to draw it, so it isn't continuous everywhere. And the point where that discontinuity is at this point here. So that might be, we don't have values on our graph, but it might be like x equals -1 is a discontinuity. So this third graph here is an example of what's called a piecewise function. And that's because it's made up of different pieces. So a piecewise function is defined by multiple functions over different intervals. So for example, we might have a function like this one here that says f of x is equal to x squared when x is less than or equal to 0. But if x is greater than 0, then our function is equal to x plus 1. So it's got these two sort of sub-functions that only apply to certain intervals. So piecewise functions, we have to look at them really carefully to be able to tell whether they're continuous or not. I want to have a look now at the more formal definition of continuity. So it's not just you can draw it without taking your pen off the paper. The formal definition involves limits. So we say that a function f of x is continuous at the point x equals a if the limit as x approaches a from the negative side of that function and the limit as x approaches a from the positive side of that function and the value of that function at the point a, all three of those things exist and they're all equal to the same value. So let's have a look at an example. So our example asks us to consider the function f of x equals 2x cubed when x is less than 0 and 4x minus 1 when x is greater than or equal to 0. So part A asks us to find these two limits and the value of f of 0. So we'll go through and do that. So first we've got limit as x approaches 0 from the negative side of f of x. So because we're approaching 0 from the negatives, then we're going to be looking at this section here because this is when x is less than 0. So we're looking at this function here, this 2x cubed. So we'll write lim as x approaches 0 from the negative side of 2x cubed. And then we'll substitute in that 0 and we will just get 0. So 2 times 0 cubed is just 0. So now we need to find these two and see if they also come out to be 0. So the limit as x approaches 0 from the positive side of that function. So because we're approaching from the positive numbers or above that value of 0, we're going to be looking at this second function here, so that 4x minus 1. So we'll write down the limit as x approaches 0 from the positive side of 4x minus 1. And we'll substitute in that 0, so 4 times 0 is 0, minus 1 gives us minus 1. So already we can see that because they're different values, this isn't going to be continuous, but we will just find that last one as well. So the last one is finding the value of f of 0. So f of 0, we're looking for that equality sign there. So because it's x is greater than or equal to 0 for this second function, that means we're going to substitute 0 into there. So again, we'd have 4 times 0 minus 1. So 4 times 0 minus 1 is equal to minus 1. So we've got 0, minus 1, and minus 1. So because they're not all equal to the same thing, it's not going to be continuous. So that's part A that just asks us to find those. B asks us to sketch it as well and then tell us if it's continuous. So we already know it's not, looking at the algebraic way of looking at things, but we'll sketch it as well. So you should use a ruler for these, but it's hard for me to do those sorts of things on this. I'm just going to sketch these really quickly up here separately. So if we look at that first function, 2x cubed, we know that that's a cubic, and that 2 just makes it that little bit skinnier than the regular cubic. So it would look something like this. And this one here, that's a straight line with a y-intercept of -1 and a gradient of 4. So we know it's going to pass through -1, gradient of 4 means it's quite steep. So it would look something like this. So that means that we only want this one when x is less than 0. So we want from here with an open circle down this way. And this one we want when x is greater than or equal to 0. So we want a coloured in circle and coming up this way. So we transfer those onto the same graph. We're going to have our open circle here, and then our cubic coming down this way. And then we're going to have our coloured in circle here at -1, and our straight line coming up here. Alright, so that's our function sketched, and you can really clearly see that it's not continuous because of these points. So we'll write therefore not continuous at x equals 0. Alright, and the last part of this question, part C, asks us to state the domain and range of that function. So that a domain is the spread of x values where that function is defined. So the domain is all real x, because even though there's a discontinuity here, because it's defined here and not defined at the top, it is still defined at every value of x. So domain is all real x. And the range? Well, the range, every y value there is covered as well. So the range is all real y. All right, so that's a quick look at limits and continuity.